trusted astronomer that is now back in the building. We're both in the building at the exact same time, and that is Marley. Hey, Marley, how's it going?
It's good. Happy to be back. Happy the sun is out. That's nice. Yeah.
Yeah, the sun has been out. It's been a bit of an odd weather. Solstice is coming up, which is kind of very strange for me because I need my darkness. So the sun is coming up very early and it's also setting very late. So I don't know what's going on with my biorhythms. How are your sleeping habits these days?
I mean, they're kind of dictated by my cat. So I am awake when she's awake and I try to sleep when she's asleep, but she doesn't let me do that very often. So the sun has nothing to do with it. It's entirely dependent on Emily.
Awesome. Well, we're back in the building, and I've missed you. We have been very busy. It's the end of the school season. We are getting ready for summer. Our planetarium is back. So if you've been in and around the Space Center recently, you know we've had some technical issues, but we're back. We've got some fun events planned for the summer here on the unceded territory of Musqueam, Squamish, and Tsleil-Waututh. Like I said, solstice is coming up, but we've got some fun stories to get to specifically about our favorite space telescope. But before we get started, you have a special message to send to someone, right, Marley?
I do. The screen share is loading, but it's my Grandma Jones' birthday. She watches the
Oh,
show all the time. She's watched
happy
since I
birthday,
started
Grandma
here.
Joan.
She is also Michael's #1 fan. So happy birthday to her. I genuinely don't know how old she is, and I wouldn't tell you if I did. Anyway, happy birthday,
Well,
Grandma.
well, there you go. Well, speaking of things that are maybe old, maybe not, but
Yeah, careful, Michael.
we're gonna go back in time. We're gonna go Huey Lewis in the News style, back in time to the very early universe. And this is something that JWST is looking at, and there's been a lot of really cool stuff ever since JWST went online last year. We've got some cool surveys and cool data and science to talk about. So we're going to get into that. If you're out there on YouTube land or Facebook land and you want to get in and ask Marley questions, put a question into the comments and we will get to it. And of course, if it's not pertaining to anything we're talking about, that's fine too. We will attempt to answer all of your questions until we get to the half-hour mark today. So without further delay, Marley, let's get into what JWST is looking at.
Well, it's one of the few things it's looking at. It's been looking at a lot. I'm biased because I like learning about galaxies. And so as soon as something happens regarding galaxies that JWST has looked at, I want to read the paper. And so the most recent one that came down, actually 3 papers were published on Monday, June 12th. So quite recently, has to deal with this Iger survey. And this Iger stands for Emission Line Galaxies and Intergalactic Gas in the Epoch of Reionization. So there's a bunch of words that are very long and mean a lot to you if you know what those words mean, which I'll explain in case you don't.
Oh, so it's not HR Geiger, it's HR, it's just Iger,
Iger, yeah.
not the guy that created the alien.
Nope. I don't know who that is. But it's not him. It's also a name in of a mountain in the Swiss Alps, I think, as well, which is where the main institution where a lot of the researchers are from are out of.
Okay, very cool.
Yes, but it is one of the guaranteed time observer programs, which I'm bringing up because I'll talk about a little bit more about those at the end. If you ever wanted to look it up or look at it, it's number 1243. And guaranteed time observations are the observations defined by members of instrument and telescope science teams. So if a researcher worked on building an instrument for JWST, if it worked on some of the science behind JWST, often those teams are given telescope time in it kind of like an exchange for their efforts. So this is one of those programs, or one of those surveys, and its purpose is to explore the evolution of intergalactic gas. So that's gas between galaxies and in the galaxies themselves during this time period in our universe called reionization. Right. Yeah, so this is long ago.
Yeah, definitely a word that we don't use often, reionization. We've put it into the actual title of this episode. What the heck is reionization?
I think it'll be easier if we start from the very beginning and work our way up. So we start with the Big Bang, right? The universe forms about 13.8 billion years ago. We're kind of more familiar with that. And shortly on cosmic scales, 380,000 years after the Big Bang, we have the first step, which is recombination. So from the Big Bang, if you think about it, the universe is very hot and very dense. It's very tightly packed into one spot, and it's expanding. But because it's so hot and so dense, there's so much energy in there that atoms aren't able to form very quickly after the beginning. They take a while to form. In fact, they form kind of at that 380,000 year mark is when we get atoms. Electrons are finally able to, hold themselves around the atom, or not being excited out by all this energy, and so they're able to stay. When electrons are able to orbit around an atomic nucleus and be latched on, that means that photons, or those light particles, are able to move freely throughout the universe, and then we get the cosmic microwave background. So that's kind of our first step. And then we get to dark ages, which is where our universe has now become this word opaque, right? Now it's dark again. And it's a little bit different from the dark at the beginning because it's dark at specific wavelengths. So when all those atoms form, the main ones that form is neutral hydrogen atoms, right? Neutral hydrogen will absorb at specific wavelengths of light, kind of in the optical and the ultraviolet, and that ends up being a part of the light that we can't see, right? It's dark to us because it's been absorbed by these neutral atoms, and they're just holding on to it. And so the universe is opaque at those wavelengths. There's other wavelengths of light that are able to move, that we're able to kind of see, but it's opaque at those. And so this period of reionization, or the era or the epoch of reionization, is this time period where we start to see the universe move from being dark at those wavelengths back to what we call transparent, where we're able to see what's going on at those wavelengths of light. And it's complete within 1 billion years after the Big Bang. But the mechanism of what kind of kickstarts it, what gets it going, is something that we weren't too sure about. The leading theory was that, well, when the first stars form, they probably produce a lot of energy, and that reionizes the gas. So it allows those electrons to be, excited out, leave the hydrogen, neutral hydrogen, now making it ionized hydrogen and letting light move through it again. So that energy is not just all locked up or locked away, is the idea. And that's what this survey was looking at. It was looking at specifically this reionization period to see if we could kind of get a glimpse of what was going on during that time with this telescope.
Very cool. And I think like one of the things that I'm always curious about, and when you're talking about this era, the first stars that formed 200 to 400 million years ago, and then you have first galaxies. Now, did those form separately? Like, was there stars kind of like free floating? Because we think of a galaxies as being like in formation, right? Like that's kind of what a galaxy is stars clustered together in a very large formation. But did that not actually happen until later?
So the stars would have formed first, because galaxies, as we define them, are collections of stars, gas, dust, and dark matter, all these things. So stars would have had to start forming first, but you would have had them starting to form, and then kind of in big pockets, and over time would become more collections of a galaxy. You have to get the dust involved as well. It's kind of one of these things of, we love to sort things, but the universe doesn't care to be sorted. And we see it later on too. Like there's at what point does a globular cluster, which is a large collection of stars, stop being a globular cluster and become a dwarf galaxy, right? It's like we draw this arbitrary line, and I'm not too sure exactly when we'll agree on where that line is, right? I think if you ask different people, you get a different answer.
And this is really cool because our last evening event that we did at Cosmic Night, we had Dr. Riley Hill that was talking about some of these very early galaxies. And we're going to be doing another Cosmic Night in September where we're actually going to focus in on stars. So stay tuned for that in September. But let's keep going with some of these other things that JWST is looking at.
Yes. So where specifically, so the team didn't look at the entire period of reionization. They looked at just before the end of the period of reionization, where the universe isn't quite completely transparent, but not completely dark. It's kind of like a patchwork of little bits of dark and places where we're able to see. And specifically, JWST was aimed in the direction of a quasar, which is this very luminous, active, supermassive black hole. So this is the survey area where they were looking in the sky. The quasar is where I've put the box. And so they looked at that quasar and in and around that quasar. In the view we're seeing now, there's over 20,000 galaxies in this field of view. And this is somewhere in the sky between the constellations Pisces and Andromeda. How big it is across the sky is about the same as if you looked at the moon and you looked at like a quarter of the full moon, is how wide this piece of sky is. So it's quite a small piece of sky with 20,000 galaxies we're seeing in it. The quasar itself is 12.8 billion light years away from us. So it's very, very far, which is very typical of quasars. And it's centered on this quasar because quasars are very energetic. They we see them very far away, very far from our own galaxies, which is good because it kind of puts them near the time period of this era of reionization where they wanted to be looking at these extreme distances. They have very bright jets that point and kind of excite the gas around them. So these are quick detour into what a quasar really is, so you get an idea of what I'm talking about. It's a type of active galactic nuclei, which, if you know me, I love them. Seyfert galaxies are another type. They are galaxies that are close to us. And so the active galactic part is that the supermassive black hole at the center is actively accreting material at the time. So Seyfert galaxies closer to us, nearby, we see their lobes kind of as like on an angle. We see their radio jets at an angle. If this is Earth, this is what we see them as. Quasars and another one called blazars, they are extremely distant. Quasars, we see their jets at many different orientations, whereas blazars, we always see the jets like face on, right? So we always have a jet pointed directly at us. Quasars pour out about anywhere between 100 to 1,000 times as much light as our Milky Way. So they're very, very bright because they're very bright and because they're so far, observing the central light source will usually wash out the galaxy it's in and galaxies around them. The benefit, though, is that JWST is very high res. It was kind of built in the right wavelength for all of this red shifted light we're going to get from these very, very far quasars, and is also sensitive enough to be able to distinguish between the bright central region and the rest of the galaxy. So it's kind of the perfect telescope to be able to do this sort of work, built really for the circumstance.
Now, but the real question is, why is blazars spelled with a Z, but quasars is with an S?
Yeah, no, quasar is stands for a quasi radio source, I think, or quasi something radio source. So it's a bunch of words condensed into one, and blazar, I think, just sounds cool.
And there's actually a arcade in Victoria called Quasars, but spelled with a Z. Okay,
well, not the same thing, I guess, but yeah, it has to do with, it's a quasi something radio source, so they just stuck the words together.
I actually didn't know that. I'm glad I asked that question, which does kind of like lead to a previous question Keith, maybe tongue-in-cheek, asked, is there a rule that every astronomy project or object, does it have to have a contrived acronym?
Yeah. It either has to have a contrived acronym or the longest name in the world that's just a barcode. So the quasar that it's focused on, this particular quasar, its name is like JD01101 plus 283, like it's just the longest name, right? So yeah, no, it is kind of a unofficial official rule that either you have a fun acronym or the name is so long.
Yeah.
Anyways, they've pointed at this quasar because the quasar acts like a giant flashlight, essentially. And so you've got all this dust and gas between the quasar and the telescope observing it, in this case, JWST. And so as it illuminates the gas, we're able to see what's going on with the gas. As light travels through it, you see it'll go through parts that are transparent, it'll go through parts that are opaque, and you can tell by whether or not the gas absorbs the light from the quasar or if the light from the quasar moves freely. And they see that using spectra, which I also love, but didn't include because it's a lot of graphs, and I didn't feel like explaining graphs today. Ask me another day.
Okay.
But also, they also used complementary data from a bunch of other telescopes on the ground, right? So it's not just JWST didn't just do all of this work by itself. It's also pulling back on data that we've done before, that we've collected before, and kind of complementing and giving us a new view to this quasar.
Okay, so if you don't have some graphs from us, then I'm going to bet that you probably have some cool photos for us then, right?
Yes, I do. So these are examples of the galaxies that they found. They're cool to me and to people who are interested in them. These are some of the galaxies. So along the line of sight of the quasar, they found in and around the quasar, they found 117 different galaxies. 59 of them were along the line of sight. So they were in that area where the gas was being excited by the quasar. And so these are some of them. They are, of course, Iger and then a number. They are all from around a time period when the universe was about 900 million years old. So 100 million years before that 1 billion mark where the universe is completely transparent again. And we can see structures in every single individual galaxy and also the other ones that aren't pictured here. We're able to see structures in individual galaxies. They're very young. Young galaxies are very clumpy and they look very chaotic. That's kind of always what they look like. But you can see active moments of star forming regions. So this kind of answers your question, Michael. It's like what comes first, the galaxy or the star? The stars come first, but they form like in these pockets, right? Well, really, I guess the gas comes first if you want to get right down to it. They form like in these bright pockets, right, where we see these bits of stellar formation, star formation. The stars that are forming are much more massive, right? They're the very, very massive stars. They form very quickly. They die very quickly. And looking at the galaxies themselves, so remember, they're in front of the quasar. The quasar is shining all this light, all this energy, and it's moving through different types of gas, right? So it's moving through it's either being absorbed by the gas or it's moving freely through the gas, which means they're able to see it. What the team found is that each of the galaxies, on average, has a transparent region around them, kind of like a bubble, right? And this extends to about 2 million light years in radius. So each one of them has about a 2 million light year in radius sphere of transparent gas or around them, which is that's like about the same distance from Milky Way to Andromeda. So quite a large distance around. Right. And what the team essentially, what it kind of confirms is this idea that essentially each galaxy has this giant bubble of gas around them that grows and grows and grows until it hits the neighboring bubble from another galaxy and it begins to combine. So this is another graphic that really, I think, kind of helps show what they're talking about. So we have stars form and galaxies assemble, and we have these little ionizing the transparent gas, around them, right? This ionized gas around them. As the stars form and as their energy, is output into the area, ionizes that gas. It just gets larger and larger until they all interact with each other. And now the entire universe is transparent and clear. And that is the end of reionization. Right. So it's trying to find this like hard limit and also the mechanism of how that happened, which is a very cool paper. This is just from paper 1. So remember, there are 3 papers that were published. This is paper 1. So the other 2 deal with slightly different stuff, like the more about the shapes of the galaxies, the morphologies of the galaxies. And then the third one, I think, deals with specifically the quasar. So what's going on with the quasar itself.
Really interesting. So what's the next step in this study of quasars?
The next step is to observe more, right? So it was kind of like a question I had was, whoa, why are they publishing so quick, right? They have 6 fields total they want to look at. This is just field 1. And it's because the data is just that overwhelmingly good. Like, it's just really, really good observations. The margins of error are quite low. It's a very, very robust data set, and it works really, really well. So the next step is 5 more observations of different quasars. This is what I mean by the names, right? So the quasar they just centered on was SDS J0100, plus 2802 at a redshift of 6.3, so pretty far. They have other ranges of redshifts that they're looking at, but they're going to do the same thing. They're going to focus in on a quasar, or what they call anchor their observations around this one quasar, and then look to find all these different galaxies and focus in on the ones that are, kind of in the line of sight of that excited gas that they're able to look at and collect different spectra. But what's good about all these quasars they're looking at is they still have all of that data collected from previous observations on the ground. So it's not like necessarily reinventing the wheel or anything. They are just taking a closer look at information we have and giving us a better idea and a much more clearer view than we've had with work previously.
Awesome. Amazing. Well, I'm going to be looking forward to the next 2 papers, and also looking at the other data that JWST is looking at. And specifically, like I said, in September, we're going to do focus on stars. And I assume we'll be looking at some of these early stars that JWST is looking at. And so if you are out there and have any questions about any of this stuff that we've just talked about, or any question under the universe, put it into the chat. We've got about 10 more minutes here with Marley. One thing I was listening to Society podcast was that there is an issue with one of the instruments on JWST. Have you heard about this?
No, which instrument?
I can't remember which one, but there's one that they're waiting for the engineers to kind of like figure out a solution for something that's doing kind of strange.
Oh, geez, I have not heard about this. The last I heard about with an instrumentation problem was Juno. Nope, not Juno. Which one? What is it called? The one that just launched? JWST. JWST.
Okay, yeah.
JWST had a problem with its antenna. Its antenna wasn't able to get out all the way, but they managed to fix it. So that was the last instrumentation problem I heard of. I haven't heard of JWST's instrument problem. Okay. That's nerve-wracking.
And also coming up, we've got, in terms of other space missions, if we're going to go through some of them in the news, OSIRIS-REx is returning in September, right?
Yes, it is September 24th is when OSIRIS-REx comes back. Well, OSIRIS-REx doesn't come back. The samples come back,
Right,
and
okay.
that's what we care about. OSIRIS-REx is missing Earth and going to go do something else, look at a different planetary body, I think another asteroid. But the samples from asteroid Bennu will be returning to Earth on September 24th, and that's the exciting part. Yeah, that'll be great.
Okay,
I hope it makes it.
Yeah, very cool. We'll definitely be talking about that. And I also just heard today as well that Psyche is actually looking good for launch in a couple of years.
It is, yeah. Yeah, that was almost a mission that was almost gone. They almost axed that completely. So I'm glad that they were able to figure out a way to go forward with that mission. Another one that I think is kind of under threat is Veritas. One of the Venus missions is another one that's kind of under the microscope for getting the cut, which is too bad. I hope it doesn't.
And it brings us to our episode that's going to be coming up in a couple of weeks, because on June 30th every year, we like to mark that as Asteroid Day. So Asteroid Day actually falls on a Thursday. So on the day before, we will take a special focus on asteroids, and maybe we'll talk about a few missions, but we're also going to be talking with a very special guest. The reason that you didn't see me a few episodes back was because I was at the Canada-wide Science Fair. One of the Platinum Award winners from this year's Canada-wide Science Fair from Toronto, Ruthie Nath, who's in grade 8, if you can believe it, and she developed a new algorithm for detecting asteroids. So she is going to be our special guest in 2 weeks, and we'll hone in specifically on asteroids. So that's going to be super fun.
No, I'm excited. I'm excited to meet her, not face to face, but meet her anyway, and also hear about the algorithm she's created. Very cool.
So when it comes to some of these missions that we're talking about, specifically asteroids, I think like that's one that's been in the news a lot recently. Can JWST help us out with it? Because I know that it's an infrared, looking in the infrared, and I know that detecting asteroids is very difficult. Can JWST help at all with that?
I know it has some observations scheduled for asteroids, so it looks at them. The bigger thing is that they move quite quickly. And so if they're moving too fast, JWST will have problems locking onto it. We saw this with some of its early engineering information when it came down. I think it was trying to track Jupiter, I think it was, and it lost guidance, so it didn't know where it was in space anymore because the object was tracking was moving too fast. It happened when it looked at DART way back when it tried to observe the DART collision, but that whole system was moving too quickly and it lost its guidance, and so it just started drifting, right? And it was kind of looking in the right direction, kind of wasn't. It wasn't locked onto the target anymore. And so that tends to be the trouble with JWST. I don't know how helpful it is to detect asteroids, like, because that's kind of it passes through the field of view type thing, or you're actively looking for them, and it's not necessarily actively trying to discover more asteroids necessarily.
Yeah. We'll get into that, and we'll talk to Ruthie in 2 weeks. For this week, we've got another question come in from Wormy Gaming. That's fun. I don't think I've seen Wormy Gaming ask a question before, but they ask, what caused Andromeda and the Milky Way to go on a collision course?
Oh, their gravity. So they're just so the best way I can explain it is if you were to like balance a pencil perfectly on your hand, you've found the center of mass, right? So it's the place where things are equal and balanced. They are being attracted to each other's center of mass, right? So they have this part where it's perfectly balanced between the two. They're both heading that way, and that's what's going to cause them to collide. It's just the gravity of the two of them are just slowing, and they're just moving kind of in that way, so they're going to hit. Just what happens.
So Andromeda, Andromeda is the closest galaxy to us in the Milky Way. So at some point, so if they're on a collision course, were they always on a collision course? Were they further away if we go back in time?
If you went back in time, they're probably a bit further away. So I think what's happened is they've just entered into each other's realms of space. Like everyone, our local group, right, where our galaxies live, is all like a gravitationally bound group together, right? You have like Milky Way, the local group, the Virgo cluster, the supercluster, right? It's just different levels of gravitationally bound stuff. And so we're just in that area with Andromeda. And so it got on our path for some reason or the other, and now gravity will kind of just take that over.
Very, very cool. There's another question I actually just thought of because I was reading about our friend Betelgeuse. In a couple of years, people are talking about Betelgeuse. I know that our previous astronomer Rachel got a lot of questions. You've been getting a lot of questions. It's back in the news again. Do you have any update on what's going on with Betelgeuse?
What did it dim again? Is that
Yeah.
what it did? Yeah. So Betelgeuse is a variable star, technically. I don't fully understand why it counts as one. I feel like there are better variable stars than Betelgeuse, but it counts as one. So its brightness does dim and brighten back up, like on a semi-regular basis. Like there's different timings that it happens at. Who knows? It's kind of the one star where it's like when that goes, we'll see it, right? But it just hasn't gone yet. And this is something I got a question recently from a group of grade 10 students who were doing a project on stellar life cycles and stellar evolution. And the question was, how do you know how old a star is, like a specific star? And it's actually very difficult to give a specific age to only one star. It's much easier to give an age to a group of stars because you have a bunch of them and some of them have evolved off of what's called the main sequence. But if you're looking at one star, it's really hard to compare it to anything else. And there's a lot of different ways, right? So Betelgeuse, when we say like, oh, it'll probably go supernova, it's really just a ballpark of when. Like there's no exact timing. It's like it could go at any time because it's our idea of how old it is very, very broad. It's a very, very broad idea.
Yeah, I love these questions that the school groups ask us because they're always like the questions that we're not asking ourselves, but like they're seeing things in the news. And they always come back to us, and I think that helps us kind of like frame kind of like what we should be talking about. And I think I actually had a group that we were talking about, age of stars and how we actually know the age of stars and kind of color and size and age are all kind of like intertwined with each other. But that's a good explanation. Another question from Wormy before we get out of here for this episode. What is the biggest quasar that we've discovered?
Oh, the biggest? So mass is hard with quasars because it's the black hole and then there's the whole galaxy around it. I don't know.
Would it be brightest?
Brightest also because there's like interstellar or what is it? Reddening. I can't remember the inter part, but like as light travels, it just becomes more red because it's traveling through a bunch of dust and it can make it redder, and so it might not be as luminous as it appears to be or as it doesn't appear to be. Biggest, I don't know, the most massive quasar we've discovered. I also don't know the most distant because there's lots. Like we find a lot. We keep finding them. And then I stopped memorizing it because then it'd be wrong. I was like, I'll just look it up. But I'm not sure. That's a good question though. The most massive one. I know that the ones they're looking at in the Iger survey are not the most distant quasars. There are quasars that are further. And maybe brighter. I don't know.
So these are only associated with really big black holes?
Yeah, well, they're the supermassive black holes. So ones at the centers of galaxies are where quasars are, and for it to be a quasar, it's an active galactic nucleus. So the black hole is actively accreting material and is like pouring energy out into the system that way.
Awesome. Well, that's about wraps up this episode of Ask an Astronomer. And hey, Shandine Peak actually watched.
Shandine, hi Shandine.
Hello, Shandine. Yes, we're going to hopefully do another event with Shandine sometime soon. Thank you so much for watching, and happy birthday to Grandma Joan. Hopefully we will meet. Maybe I can meet you sometime in person. That would be very lovely.
She would be so thrilled. Genuinely, it'd be great.
And of course, I gotta say hello. I need to shout out to my mother as well. I missed Mother's Day because I went to the Canada-wide Science Fair in Edmonton. So I owe my mother Sharon a phone call. It's just been very busy.
Oh, her flowers, Michael. Missing Mother's Day. Goodness.
For science, right? And we will talk with Ruthie Knapp in 2 weeks in celebration in memoriam of Asteroid Day.
Well, I think nothing. I don't know. It's kind of in recognition.
Dinosaurs.
In recognition of Asteroid Day.
Yeah.
Yeah.
Well, actually, I suppose it was like because nobody actually died during the event in Tunguska, right? We don't think anyone died anyway, but that's the actual date. That's why they picked that actual date, because it was the Tunguska event. So anyway, Arushi Nath, grade 8 student from Toronto, is going to be our special guest June the 29th, 4 p.m. Pacific time. For me and Marley here at the MacMillan Space Center, we will see you all again.
Bye-bye.